Sasha mentioned a little bit about live code updates, but I wanted to tell you, basically the motivation for it was we wanted rapid code iteration for JVM and Android development, because we found that whether it's deploying to a small device or deploying to a server or even just a desktop application where you need to get it back into a particular state, it was just taking too long to go between making a small change and then being able to play with that change in your application, because developer iteration speed matters. So we initially started this for Hack Week last year. This is something that we do twice a year. You take a week and decide on whatever you think is the most important thing that you should be doing at that time, and then try it out and see if it's something that could go further. And this ended up something that we kept working on along with other projects. An important thing is that we do arbitrary updates to programs. It's not just method replacement like you can do on the JVM. You can restructure your classes, change the class hierarchy, add new fields, remove methods, whatever. Within reason, of course. Because some things, it's just, if it's a completely different program, it doesn't make sense to consider it a live update. And there's no built-in support on Android. So the standard workflow that we're all familiar with, you compile your program, then there's the linker phase, you deploy it to a device or a service, you restart the service. It has to, especially for services that have to reconnect to other services, there might be lazy calls. Eventually the initialization finishes, get back into the state you're in. It typically takes a couple minutes, could be longer if you have to provision a server. And what we want to do is be able to make a small change and then have it update in a few seconds. And that's what this system accomplishes. So the basic flow will be, first I'll give you a demo. Actually, I'm going to run a demo that's on my computer because I figure if I just have it on an Android device, it'll be hard for you to see it in the back. And then I'll show you a video of the same kind of thing running on Android. And then we'll go over how it works in some detail. So let's see. So I have this bouncing ball program. If you look at the overview of it, we have the main that just opens a swing frame. There's some state in here for the X and Y position of the ball, the DX, DY, its velocity, and its size. And then what we do is we set up a timer that just periodically updates the physics, meaning moves the ball, and then also repaints the ball. And so what I'll do is I'll run this initial version of it, and then I'll make some changes to it. So all right, so we have this red bouncing ball. Let me make some room on the screen here. And I had some code in here to just change how it's drawn. So for example, maybe we'll change the color of the ball to be green and add a little bit of additional design to the ball. And then I just do a live update. Tests. This is a lot quicker when you have two hands to type, by the way. Okay, so it compiles the update and then it applied it. And you could see it just kept bouncing on the same trajectory because we had the same object instantiated as opposed to starting with a new one. And there's nothing in this code for actually serializing itself or anything like that. It's just very simple code. I have another version in here. Let me just put this down. Basically, what I'm going to do is I'm going to go through a few different versions of this code that make different kinds of changes. And I'll tell you what the change is when I get to that version. So I'll just switch between talking and typing. Okay, so I'm just looking at the diff here. What I wanted to do was I wanted to change the velocity of the ball without actually stopping the program. So I just added this variable in as an additional field in the class, and then I just say the first time it's 0, and then that's where I do the update, also update what the version is, so then after that, it just keeps its velocity. Because if you just keep setting the velocity to a particular thing, then it'll just go off the screen. It has to bounce at the edge, you know. So we'll run that update. So, you know, just a few seconds, and it's like that. The interesting thing is that you get the same kind of performance also, whether it's on a remote device on Android, or even if you're building on more complicated frameworks like our Scala web frameworks. Let me show you one more interesting update, which is to actually introduce a new class that wraps around the ball. So we're going to actually change the structure of the code, get rid of some methods, change where the state is located, and we'll still have a seamless upgrade. Okay? Okay, so in this new version of the code, I've added this variable ball and this class ball. The class is defined down here. So I actually moved these methods, update physics and paint, into this class. And since some of my objects won't have that ball initialized, I just added this if statement here to initialize the ball from the existing position. And then after that, it'll be initialized and it'll be running the new version of the code. Okay, and so that applied, and again, this is just a couple seconds. So let's move on to the video of the Android version, just so you can see that we weren't making that up. So I had the Android Studio IDE there, and then this little window up here was an extension that connected between that and the Android device wirelessly. So it's the same protocol as what I was showing between those two tabs there. And then when I hit the button, you saw it updated from the red to the yellow shape. Same exact approach because it's basically the same code running on both platforms. Okay. So now the question is, how does it work? So if you look at some code, you might have some kind of structure like this where you have a base class, maybe it's called entity, something from a library, and then maybe you have two different subclasses of that, call them like geoplace and Twitter user. Because I used to work on some ads geo-targeting stuff here. And if we want to be able to update these, the thing is, if we already have an instance of Twitter user in memory and we want to add some additional fields to it, we already have that somewhere in our object graph on the heap. And for just normal code in the JVM, we can't go there and find all of the objects and replace them with other objects, because then we have to find what references them. It can be quite complicated. So we have to have some other approach to do this. And basically the transformation, what we do is we transform the code. So instead of making any changes to the VM, we make changes to your code so that it has the right levels of indirection, so that when we're ready, we can swap in the changes that we need. So for example, this code gets restructured to something like this, where let's start over here. This entity class is still the same thing because that's something that came from a library, or maybe it's part of the Java-based APIs. So we don't change that. But then instead of having two different classes here like geoplace and Twitter user, we have this one class. Actually, there's a typo here. This should be ipipe entity. What this means is that any class that's in this part of the code that you're going to be updating that happens to be a subclass or an eventual subclass of entity, the instances of that will actually be represented by this kind of class. And so this is basically a representation for the class as opposed to just having an instance of the actual class. So it has this class ID that says, oh, maybe class ID 15 means geoplace and 38 means Twitter user. And so there has to be some kind of lookup mechanism to resolve, okay, if we have something with the ID of 38 and we get some kind of method call, like maybe this is, maybe the entity implements runnable, and so there's a run method, then somehow we have to run the run method code for Twitter user, and not just for some version of Twitter user, but for whatever the current version is of that class. And the way that it works is that basically this is a proxy that delegates through it to this global array where it does a lookup from the class ID to whatever the current implementation is of that class. And that implementation is something like this here. There's some base class for these different implementations of the methods for entities. And then we have this Twitter user, M is for methods implementations, and 0, that's the first version of it. So like when I did the updates 3 times, we can actually look in the directory there, there'll be different versions. Baster. Yeah, so right here, you can see this bouncing ball view. The $1, that's just a Java thing saying that it's an anonymous inner class. But then you can see there's version 0, 1, 2, 3 from the different times that I reloaded the code. And the way that we actually manage this is that for these basically different sessions of your code, we have the classes that implement the methods in their own class loaders for the different sessions. And so if you've completely overridden the versions of the classes from the previous session, then the only references to those were in these purple objects. Like on your heap, you don't actually have references to these things. The only reference is from that global array to one instance of that class. So that allows the garbage collector to actually say, hey, all of the classes that were loaded in this class loader are no longer referenced, so I can actually get rid of them, and it doesn't end up cluttering up the permanent generation. Which, and I mean, it works even better in the newer VMs that don't actually have a permanent generation. So concretely, here's an example of this instance proxy like this over here. So if we were to write that out as Java code, although it's actually directly generated as bytecode, it has this class ID integer. It has a hash map called fields. Now, I didn't mention that earlier because there was a bunch of other stuff going on. But what we do is all of the fields that you inherit from the base class that's a system class, for example, if you have, well, I don't have a good example, but basically you have some kind of system-based class that it has an int and an object reference in normal fields. Those remain as normal fields so that we don't have to modify that base class code. But any additional fields that you add in when you extend it, instead of going in as additional fields, get put into this hash map. The reason that we're using a hash map right now, as opposed to, say, just an array, is because let's say you have some kind of system class, then you have A that extends that, and then you have B that extends A. So you have this instance of B somewhere. And then you add some additional fields into A. You need to know where to put those fields. If you just had an array, then you'd be like, well, maybe we can hash it, put it somewhere, and then you realize, oh, you have a hash map. And an additional thing that we have here is instead of always calling things directly as methods, because there's some methods here that are inherited from object, so we can override all of those. But there are some methods that object doesn't have that you extend, and you don't know beforehand what methods you'll be adding. So we have this dynamic instance method that allows us to say, okay, this is some method that is only known in this user code. Like let's say if on Twitter user, if it had a method like something like capitalized name, where it does appropriate capitalization. We didn't know about that beforehand, so we can't encode that into this base class or into the proxy, so we have to use a dynamic dispatch method where we say, okay, we'll have an integer that specifies that particular method ID and then the array of arguments, very similar to what you have with method objects in reflection, actually. And then a second thing that's important here is dynamic super method. This is for the other direction, where if you have some code that you've written and it has a super call. And that code is now a method that's on this mpipe Twitter user pipe 0 object. If you were to just do it as a super call, that would try to call a method that's over here, whereas you want to call a method that's over here on that entity class. And so you need some kind of protocol for it to say, okay, I have a reference to one of these, and I need to call it a super method. And a different object can't call a super method in Java. So this is kind of how we poke the hole to allow a different object to do that. Now finally, for these methods that you can override, generally you don't override all of them. There's some of them you choose to override, but you might say, I'm fine with using the default hash code, or I don't even use clone, so I'm not going to override that. And so what we do is in this methods implementation class, in addition to having methods, we also have bit fields indicating which of the inherited methods you actually override. So when that method gets called, like let's say hash code gets called, the first thing that it does in this proxy object is it says, okay, give me the methods implementation object. All right, I have that. Now look inside and tell me, does it actually implement hash code? If it doesn't, you call the super version. If it does, you call its version. Okay? Does that, yeah, do you have a question? Okay, so the question is, since we're swapping out classes for classes effectively, what happens if you change your inheritance hierarchy? And the important question to ask is, change it in what ways? There's some kinds of changes that you can support and others that you cannot support. Right, so let's say you add an interface to a class. Let me first address the first point and then add that to it. So if you, like let's say there was some system-based class, let's say there's exception and there's abstract list, and you had something extending abstract list and then you wanted to change it to an exception. That's something that you can't do. It just doesn't make sense because the rest of the program, who knows where it has a reference to this thing, and it thinks it's an abstract list. If it becomes an exception, then you're breaking your memory safety guarantees. So you can't do that. And so that's checked statically that you're not doing that. On the other hand, you might have something where, let's say you have classes A and B, and we have like A extends entity and B extends A, and you just want to swap A and B. And these are both in the space of the code that you're modifying here. Well, that means, first of all, that the outside code doesn't know about this. I mean, unless it's through reflection, but kind of when you're looking at things through reflection, you can say that you know what you're doing, hopefully. But if you could just compile this part of the code, and it's still consistent when you switch those A and B, so that all of the other code is okay with those being switched, then you can actually make that take effect. Whereas if you have code in there where when you were to switch the two, it would no longer be consistent, then you have to say, no, block this change. And so what we do is a slightly relaxed version of that, which is we don't compare the two different versions. We just say, is that later version consistent with itself? And if it is, we'll say, okay, let's try deploying that and trust that this is what the user wants to do, because it's not affecting other libraries that they have no idea what they're doing. Okay, and then the second question was, let's say in particular we wanted to take a class and add an additional interface that it implements. The interesting thing with that is we can do it in some places because you can actually invoke an interface method on an object which you don't know beforehand whether it implements that interface. So in some cases you can do that. Basically, if you're going to produce a new object, then you can produce a new one that's some subclass that implements that interface and use it with other code that didn't know whether you would or wouldn't implement that. But again, if you have something that's already on the heap, then let's see. Yeah, so if you have something that's already on the heap, then you already have an instance that doesn't have that method, like run, for example. And if you're going to say that now it has run, and then you pass it to something that thinks it has a run method, but just concretely it doesn't have it, it won't work. Yeah. So that's a good question about what the bounds are of what you can do with this kind of approach. Yeah. Second question, yeah. Yeah, so the question is, do we have to rewrite type inference, something like that at the compiler level? And the answer is no, we didn't have to do that because we're still relying on your source code being the same language and the output of that being standard Java bytecode. And what we're just doing is we're compiling bytecode to bytecode that has an additional level of indirection in it. Right, so you can't just make a new overloaded version of a method that didn't even exist anymore and rely on other code that you're not compiling at the same time to find it. If you're compiling it at the same time, then it'll just recompile both of them. Okay, any other, yes? Okay, so the question is, as we change a class, we might change what its fields are, add new fields, rename fields, remove fields. And so how does that work? Let me just discuss that right now. So in the demo that I showed you, I had a couple steps where I added new fields. One of them was I added this generation field, I think, where it was, if it was generation 0, then it assumed that the velocities were old ones that you can override, and if it was 1 or higher, then it assumed not to touch it. And then the second was when I added that ball class and an instance of the ball class. And in both of those cases, they just took on their default values when these fields were added into the class after the constructor had already been called. So by default values, I mean 0 or null. And so the way that it is right now is if you add new fields like that, then you're responsible for initializing them at whatever point. You could imagine a system where you have something similar to a database migration, where it defines some kind of a function from the fields of class version 1 to the fields of class version 2. But the question is, how difficult is it for you to actually define that when you're programming? We would have to have a really quick and easy way for you to define what that mapping is. And because if it takes too much time, you might as well just restart your program. You could imagine something, for example, that monitors your interactions and sees that, oh, this was just a rename of the same field versus this is a completely different field that happens to have the same type and does different things in those cases. But we haven't implemented anything like that. That might be an IDE plugin. Yeah, so the question is, what about the performance implications? And definitely we're adding additional levels of indirection, and if we do that too much, then it becomes too costly. There's a few important places to first consider where this happens. One is method call indirection, because we have this additional level in our method calls. For example, instead of directly dispatching to the implementation of hash code, now we have hash code on this generic proxy object that dynamically chooses which one to dispatch it to. And then the other thing is the overhead of the fields hash map. At this point, we haven't done any real benchmarks on what the impact is of these, but I would think that the fields hash map would have the bigger overhead to start off. And so there's a few things you can think about for how to improve that. One is maybe you have a compact representation initially, and then have some way of finding those things and then relaxing it to a non-compact representation just for the classes that you update. That's one possibility. You might also just have something that's a better layout than using a hash map, like, for example, a hash table that's hand-coded to use integers as keys. The other thing, though, is just making sure that you're only applying this rewriting to the classes where it matters. And I think that's the biggest source of gains, and that's something we already built in, which is basically all of the stuff that's the libraries that you include, whether they're system libraries or libraries defined within your organization. We can keep that separate from the part of the code that you're working on. And right now, we just use a really simple strategy of saying, we'll instrument in this directory and its subdirectories. And at least for the way that the code that we work with is organized, that actually works quite well. Certainly, if you had something like some kind of heavy numerical algorithm, this wouldn't be the right solution for trying to experiment with that. Okay. New object. So over here in the constructor for this proxy, you can see it takes something called new object. And I don't know how many of you are familiar with the way that object construction works in the JVM, but the basic idea is that first you construct this you allocate this uninitialized object. There's an instruction for that. Then you set up your arguments to the constructor. Then you call the constructor using, it's just like another method pretty much, but with the invoke special instruction. And then inside that constructor, it has one section where it has fairly limited access to what it can do. Then it calls the superconstructor, and then after it's called the superconstructor, then the object is almost fully initialized, and then any other final fields you initialize, and then it's considered to be an initialized object. And what we do is we transform our code so that at that point where we would create that new uninitialized object, where all it has is, it knows that it's going to be an object of some class C, but it's not usable as one yet. Instead, we construct an instance of this class called newObject, where it knows what class it's going to be an instance of. And interestingly, it still has to have the fields available, because in the Java bytecode, you can actually write to fields before calling the superconstructor, although in Java, the language, you can't. So this is kind of the core of the object. It's set up, and then if you have some kind of inheritance hierarchy, like say we're making a geoplace, so we take the constructor, transform that into a method on geoplace, on this mGeoplace pipe 0, and inside there it does the code that happens in the constructor. At some point it gets to the superconstructor call, and that gets switched into actually constructing an instance of this proxy class where it passes in that new object. So basically each concept that you have in the JVM, we have a simulated version of that that has admittedly a bit more overhead. And I might have an example of that later. Okay. So the overall system architecture when you're running it on your machine or machines is we have this orchestrated by a build system, and then there's a plugin in there for live code updates so that it can run some additional post-processing on the code between when it's compiled and when it's deployed or put in a jar or whatever. And then once you have the thing running on whatever kind of host you want, inside of there you have the application, of course, and then we have some additional runtime code. And this runtime code is able to communicate with an update service. So when I was running the update command, it was running the compiler in that same terminal, then building this update patch, and then sending it over the network to the runtime host, the host runtime, which was then responsible for updating the implementations of the classes for just the part of the code that is managed by live code updates. So the way that the update service works is, first it gets the class data for all the classes that you've compiled, the inheritance, the fields, the methods, all that stuff. And it generates these base classes for the proxies and the base class for the different method implementations. And then for the actual user class implementations, it post-processes them into something which I'll go into more detail in a bit about what those post-processing steps are. And then it serializes all of this metadata and creates overlay jars from the generated classes, sends it over the network to the runtime. Then the runtime receives the update metadata and the overlay jars. So this update metadata is things like saying that this particular class is identified by this ID, this particular method is identified by that ID, so that we can just use these IDs for binding things together. Then it creates the class loaders, like I mentioned earlier, so that we can separate what's loaded where. It creates the actual instances of those class implementation objects, registers them in the table that I mentioned. Well, 5 is registering in the table. 4 is registering the mapping between the IDs and things like class names and method names. And then here's an important thing. So initially what we were doing was when we were constructing the methods objects for particular classes, we were calling our post-processed version of the static initializer. And coming from Java, it seemed like, okay, that's fine. Whenever the class gets loaded, that's when the static initializers get run. It turns out that a lot of Scala code relies on the order in which static initializers of different classes are run. And so that just broke these fairly large Scala programs we were working with. And so we had to make sure that instead we actually detect not just that, okay, we have a patch for this class or we have this class available, but we detect when is the first time that someone actually references this class, whether it's instantiating it or just referencing its type because you're going to try to cast something to it. And then at that point in time is when we run the static initializers. And that was one of the keys for actually making this system compatible with Scala. Okay, so I mentioned earlier that I would go into more detail on post-processing the user class bytecode, and that's what I'm going to do. So there's several passes. As I mentioned earlier, it's basically a compiler from Java bytecode to Java bytecode that introduces this level of indirection. So the first thing that we do is we convert all the field accesses to use the hash map. So there's particular instructions in the JVM like get field, put field, get static, put static, and those are just changed. So that introduces the level of indirection for storage. Then we make all of this arguments explicit. So because we've separated out the object that's on the heap from the object that actually holds the methods, we have to get the object that's on the heap and use that in place of this, because otherwise we have the wrong this. And then also generate the dynamic instance method, which is basically for methods that are just defined within user code the way that one object can call another object, even though the proxy interfaces didn't know about my method called whatever. Then we actually convert the method calls to use this mechanism. So that's all the different method call instructions. And part of that is the constructor calls. And then we have to convert the constructors, convert the constructor calls. And then we also convert other instructions that deal with the types of objects. Like new, it has to create an instance of that new object thing. Or check cast or instance of, these are what operate on the type hierarchy. So it has to take a proxy object, take the ID of its class, go fetch the metadata, and then do some kind of comparison to see is one of these a subclass of another. Then we have to convert the constructors themselves. I mentioned this earlier, how in the phases of construction of an object, you consider this in slightly different ways depending on how initialized it is. And then we generate something called getInstance base class. That's basically if you have this, the ID of a class, and then you have that methods object, then you need some way to say, okay, now I want to make an instance of that. So this is just how it supplies that link. And then finally something called getPClass, which is used for simulating reflection. The reason that simulating reflection is necessary is because we've made all of these changes. We've taken classes and split them up into different parts all over the place. And if you were trying to do reflection on one of those proxy objects, it would look completely different from what you expected. And so if you have programs that build on Juice or something like that, they're just not going to work. And again, a lot of our Scala web frameworks, I think, all our programs based on our Scala web frameworks are just bound together with Juice. So we had to do that to make it work. And then finally, we just rename the user classes so that they're in our own package path. So I mentioned object construction informally before because I'd forgotten that I have some nice figures. But it's kind of confusing, so maybe this will help explain it. Also, I didn't update the names in these. So I'm just calling this user class and base class. And so user class A was originally a subclass of base class. But now in the graph, we have these two different parts of the graph where user class A, we have this M-pipe user class A, which is just this methods implementation class, and then over here, the instance is just a completely different class. And somehow we have to have a constructor in here where we need to construct one of these, but the constructor code is in here. So we need some way to tie those together. And so what we do at the instruction level in Java bytecode is we take something that's like new user class, and this is what I was describing earlier with my hands. Instead, we say new object. So this is kind of like uninitialized at second order. It's an uninitialized new object, which when it is initialized will represent an uninitialized user class object. Okay? So the convention is that you take the uninitialized new object, you make a copy of it on the stack, you load the arguments. So in this case, the only argument is the ID of this user class. So that's just going to be some integer. And then this is where the constructor of new object gets called. Invoke special new object.init. This constructor is implemented in the bytecode level as actually a void method. That's why we had to make a copy of the original instance. Anyway, at this point we have a new object that represents a user class, whereas over here we had an uninitialized user class. So these are equivalent. Okay, the next thing is after you've constructed an object, or allocated an object, then you make some arguments and you call the constructor. And then after that is when it's truly constructed. So before we would have this invoke special user class.init and whatever arguments. What we have instead is, well, we have that new object on the stack, and then we take, okay, give me the ID of this user class, because somehow I'm going to need to find that constructor method. Okay, I have the ID. Then I say invoke static ma.getClassImpl. This is actually short for method accessors. It's just a class that just has some static methods, utilities, that basically do lookups in that table of the implementations of the different classes. So what we're doing here is we're saying, here's the ID of it. Now, and then that's an int. Now get me that class implementation. Then cast it to the appropriate methods class. And then finally, we actually call this new instance method. So we took the constructor and we renamed it new instance. And we have a version of it that has the correct arguments that you would expect. And the first argument, instead of being this, is that new object instance. And the other thing is that it'll actually return this ipipe thing, so the implementation proxy object. Okay? Then when we're in the body of the constructor, before the superconstructor, we just use that new object in place of this. And then at the superconstructor, we call either, if the superclass is also a user-defined class, we call new instance there. Or if it's actually a base class, then we construct it at that point. And then after the superconstructor, we have this actual constructed object to use in place of this. Okay? Good so far? All right. All right, so reflection. So as I mentioned, post-processing breaks reflection. For example, juice, or you could even have like an annotation for HTTP request handlers. Like you say that, oh, this method is, it's like a post to the such and such URL is handled by this. And so we need some way to bridge this gap so that if you have some code that's going into your class, it wants to enumerate the methods and see what their annotations are, that we fool it into thinking that it still has a class that has those methods that it would have had if we hadn't done the post-processing. And each of those methods has the annotations that it would have had if we hadn't done the post-processing. And so we simulate reflection. So basically we take the whole reflection API in Java, with things like java.lang.class, java.lang.reflect.method, and all that. And we have copies of that. They have the same kind of methods on them, same or equivalent types, just in a different hierarchy within our namespace. And we prefix them as a V to indicate virtual. And so there's two different subclasses of each of those. There's the W subclasses, which are wrappers. So basically, if we change everywhere in a program to use VClass instead of class, and then we want to take the class representing java.lang.integer, well, we just take an actual java.lang.integer class and then wrap it in this W class thing. Whereas if it's something that we've post-processed, like the hypothetical example of some kind of class whose methods are used as HTTP request handlers, then what we do is, before post-processing, we get all the metadata that we'll need to be able to supply for reflection, and we build it into a different version of VClass, a subclass called PClass for post-processed class information. And so it just mimics exactly what would happen if you were talking to a class of that unpost-processed version of your code. And to actually do this, we use the Java agent parameter on the JVM and a class file transformer so that almost all the code, not just the code that the user is working on, but actually the code in the libraries also gets changed to use this VClass, VMethod, stuff like that. But it's a much lighter rewriting because all we're doing is we're changing the names of the classes that it's referencing. And also, generally you use reflection just for setup time stuff, things like that. So it's not as much of a runtime concern. And we haven't done it yet, but we could also do the same thing, possibly statically for Android. Fortunately, since reflection is fairly slow for use in Android applications and your number of methods is limited and so on, people tend not to really use reflection as much on Android. There's some cases where it's important. For example, if you want to specify a new activity that you want to dispatch to, you actually pass a class object representing the class of that activity. And for special cases like that, we do already have support in place. Okay, so in a little more detail, like I mentioned, there's the postprocessor pass that generates these get p class methods for each user class. So what happens is basically when in your code where you would have written, say, my class.class or class.forName my class, it gets replaced with a call to this get p class, which then takes the metadata that's serialized in there for not just the class, but also the fields and the methods and the constructors that are part of that class. And at that point, it actually generates this hierarchy of our simulated reflection objects. So if you're not doing any reflection, then there's no runtime overhead. Okay, and then that's it for these slides. Yeah. Okay, so the question is, what's the interaction between class loaders and thread locals? So honestly, I haven't really experimented with the impact on thread locals. The reason that I don't believe that it's a major concern here is because the actual objects that we have on the heap, we're not, say, like let's say there was version 1 of class C and version 2 of it later and version 3 of it later. All 3 of those are actually on the heap going to be instances of the same class. They're not going to be instances of 3 different classes. Yeah, so the question is, what are the major highlights or differences between live code updates and JRebel, which is a commercial system that's been around for a while that aims at similar ideas, basically live updating your program. And one of the main things is just what platforms and frameworks are supported. So there's a certain set of frameworks, especially Java frameworks, that are well supported with JRebel. And then as we've been developing live code updates, we've been developing it for our own needs, which are more like particular Scala frameworks, some of which are in-house, and Android, neither of which are really supported or seem to be a major interest for JRebel's developers. Another thing is just kind of over time how we got to where we were going. It's interesting because I looked at JRebel kind of afterwards and realized we had evolved into the same thing. Not the same thing, but kind of working on the same problems. But initially what the idea was, okay, you have an Android device. Wouldn't it be nice if we had something like the Scala REPL for manipulating our graphical programs so that we can experiment with them? And we quickly realized that, wait, you can't just have it as a REPL because you have persistent state there, things that you're interacting with. So you'd rather have some kind of way to live update your program. And then it kind of fell into the same kind of problem that we're solving, just for a different class of applications. The question is, are we planning to open source this? And we'd like to move in that direction. We don't have the time to work on that and completely assess it right now. But yeah, we'd like to do that. Okay, so the question is about spring-loaded. I'm not too familiar with spring-loaded. I know that in a lot of the web frameworks, there are ways for loading new versions of classes. For example, you have one version of your handlers for requests, and then you rewrite your code, and then you have a new version of it. The big difference is that these request handlers for web requests are stateless. All your state is either in the database or it doesn't have a state at all. And so you can easily just create a completely new instance of the class in a new class loader and discard the old one and know that it'll work. The difference here is with live code updates is that it works well for things that are stateful. Okay, so the question is, how long did it take to develop this and how many people worked on it? So there were points in time where there were additional people helping us, but mainly it was me and Alberto over here. So I worked on the core parts of it, and then Alberto worked on a lot of the build system around it, test infrastructure around it, things like that. Both very important things when you're doing heavy modification to the code that's running. So the initial phase of development was basically there was 1 month where we were working on it very much part-time, you know, like here and there in the evenings leading up to Hack Week. And then at that point, we realized the implementation we'd been doing, the approach we'd been taking, which is not what I described here, just wouldn't work. Then there was another month where we had more time to focus on it. And even that, you could say maybe it's like 1/3 time. And then we got to the point of the demo with Android. And then there was some time elapsed, and then in the fall, over the course of, let's say, about 2 months working solid, we worked through a lot of the different corner cases with Scala and stuff like that. Yeah, so the question is there a limit to how many updates you can do? And in practice, I would say, yeah, there probably is, both for resource reasons and also there's some kinds of updates that are more convenient to do by restarting your program. I did a little experiment where I tried with a very simple program on Android doing updates, and I was able to do about 900 of them. That was only reloading a few classes each time, you know, maybe like 5 classes. On the JVM on the computer, you would expect more for 2 reasons. One, because Android doesn't do any kind of GC on its classes at all, whereas if you have the right properties, then you can do GC on your classes on your computer. And 2, just you have more memory on your computer. Okay, the question is, can we roll an update back? And if so, what are the characteristics of it? We don't have specific support for rollback because we don't actually do any kind of checkpointing. We're just kind of implicitly able to upgrade things. And so the only way that you can really roll things back is if you haven't made a breaking change to basically to your heap graph. Yeah, what are the implications for multi-threading? So synchronized blocks are not going to be affected because, well, synchronized, you're locking on some object and you still have a persistent object that you're holding the lock on. Volatile fields, those are not really handled at this time. We're just putting them in the hash map. And so if there's differences in how that would work, like if you have some kind of lock-free program or something like that, that's not going to work well. But that's the sort of thing that you wouldn't expect to work well in a system like this. And if it's just a simple thing you're talking about, like you have a few threads running and you want to make sure that things are consistent when you do an update, at the level of the actual update, you know, swapping in different implementations into that table, that's done atomically. But you do always have to think about if, say, a thread is in the middle of a method that's in one version and then another thread gets into a different version of that method, then you can have a temporary inconsistency. Or if you have a method, say, that's long running, then we don't do any kind of thing where we can upgrade a method that you're currently inside of. It'll only be upgraded the next time that you call the method. Yeah, so the question is, if you're inside of some method and you're, say, in version 1 of that method, and it relies on other methods that it calls in version 1 that are not present or work too differently in version 2, is it going to break? And yes, if you're staying in that version 1 method for a long time, then it would break. So it's something you'd have to be aware of. The question is, can we deploy WAR files? And I haven't really done anything to look at WAR files. I don't even know exactly what they are. Is it a combination of a jar file and resources? So I'm sure it could be made to support that, because it seems like the major question there is updating resources in addition to the code. But there isn't special support for that right now. So this question is, can we identify potentially breaking changes and then keep them from happening? And the answer is, we identify some of them, not all of them. There's more that could be done by more static analysis. The reason that we don't really identify them is because right now, statically, we don't look too much at what the relationship is between different versions. We just look for consistency within a version. Yeah, so other applications besides developer iteration speed. So there's a few interesting areas we've looked at. One is, in addition to iterating on the program that you're working on, we could make it easier to both iterate on and just build test cases, because oftentimes when you're building test cases, you have to build a lot of boilerplate to get something into the right state, and you might just mentally feel like, okay, I'm going to have to write all this code and then run it, and then I'm not even sure if it's going to get things in the right configuration because I'm trying to test things in the first place, so I'm not 100% sure how something works. So if we can combine the model that you might have in a REPL where you're interactively experimenting with your system and the libraries and services you use, with something where you've actually persisted your program and you're able to go and modify the program that you're interacting with, so alternating between adding to your test case and fixing your program, then we might make it easier for people to build good testable systems. Another interesting thing that we've looked at is we had the question, in what way does live code updates relate to production systems? Obviously, with all the performance overhead and other caveats of being able to make arbitrary changes to your program, you don't want to be doing that to live systems like file servers and things like that. But what you could do is two things. You could think about how do I capture enough information out of this system that I've already deployed? So maybe we would have a more restricted version of what we do in live code updates, maybe just using the actual JVM method replacement system so that we don't have as much performance overhead, and just allow, say, introducing certain kinds of additional logging, profiling, get more information out of the state of a system so that you understand why is it in a bad state, or how would I get a system into that state. And then secondly, take that information and use that to build a modified version of your program that just goes straight into that state. And then run that in a test environment and swap out that setup code for the actual original code that you were running in production. So now you have basically a copy of what you had running in production, but you can experiment with it, change implementations of things, and see, okay, if I were to change this, would that help the system heal itself, get out of a bad state? And then you can say, okay, maybe the next deployment of that production system, I'll add these features after I've done appropriate testing. And then one other thing that would be interesting is, let's say you have something that's kind of in between development and production. So it's not a real-time service that somebody is hitting, but it's not just something that you're playing around with on your computer. And a good example of that is some kind of a multi-stage data pipeline where there's, it might run for an hour doing one kind of processing, and then it does some other processing and so on, like on a Hadoop cluster. And if we could say, at a certain point in time, we see that, okay, these Hadoop nodes are failing, let's just pause the system at that point, still have the data to supply to them, and now experiment with the part of the program that runs at that stage. You can experiment, make changes to it, get it into the state that it's doing what you want, and then continue. And that's also developer iteration speed, but in things where it's not between minutes and seconds, but between hours and minutes. Mm-hmm. Yeah, that's interesting. So the question is, if you think about web frameworks where you have kind of the stateless service and then the state is in some kind of back-end storage, and then you think about what we have here, is there some kind of analogy where we're automatically converting a stateful program into a stateless part and its state? And yeah, I suppose you could say that because we're saying that the state is these proxy objects that are in the heap graph, and then the stateless part is just the methods themselves. Another analogy, I guess, instead of going up the stack, would be going down the stack, is just comparing it to, say, having, well, like let's say DOS programs in the 80s where you might have stuff that you have in memory and then you have overlay files with your code and you load a new version of that overlay. It could be for a different part of the code or it could be for the same part of the code.